guys. Today we are going to discuss activity 10, which we would normally be on. It's called comparing colors. And so at this point in our wave unit, you have talked about waves carry energy, transmit energy, and they do that by vibrating particles. And sound waves are mechanical and they need to vibrate actual particles, so they need a medium. But electromagnetic waves are a little bit different. Light is in the electromagnetic spectrum, and we're going to take a narrower view, a more specific view of that electromagnetic spectrum today and talk about visible light. And with the visible light we're talking about the visible light to human eyeballs and what the characteristics of that are. And this background is beautiful because when we think about rainbows and we think about light breaking into different colors, one thing I'd like to point out and remind you of is when you study light in physics, the characteristics that we will describe is different than ink in art. So the colors in art that are actual ink have different characteristics and act differently than electromagnetic waves. And that is what we will talk about with light today. You're starting with, why is there rainbows? What is going on? Why is light divided out into different colors? So think about that for a minute, and then you're going to record a prediction. Remember, your prediction is correct. I'm just going to read through those, and no matter what you say, I will give you points for. I just am looking for, what the heck is going on here? What is light in a rainbow? What's going on? So activity 10 is comparing colors. Comparing colors, our goal is to, how are the colors of the visible light spectrum similar to and different from each other of that for those electromagnetic waves. So we know there are electromagnetic waves. We know that light, visible light, is divided into different wavelengths. That is how the electromagnetic spectrum is divided out. I will challenge you when you look at an electromagnetic spectrum online, when you do Google searches and when you get to high school, find out how they've oriented it. Is it largest wavelength to smallest or smallest to largest? And when I Google searched, my brain wants it to be radio waves on the left for some reason, but oftentimes gamma rays will be on the left. So if your radio waves are on the left, you know that this spectrum is showing you the different waves from largest wavelength all the way to smallest. So that's one thing to be cognitive and cognizant and pay specific attention to detail of. When I take out this visible light spectrum here in the middle, so you'll notice my big waves, radio and TV. Microwaves are actually pretty big waves compared to infrared. And my visible light spectrum, so you'll notice this really narrow range within the electromagnetic spectrum. And when I take that narrow range and I widen it, I can see that I have about 700 nanometers small wavelength is red. So when I look at this, I can see 700, 656, 555, 454. I see this range of wavelength, and I notice that the largest wavelength is red and that the smallest wavelength is violet. So there's our Roy G. Biv from elementary school. Red, orange, yellow, green, blue, indigo, violet. They just left the indigo off here. You know it's there. Once I get beyond violet, it's called ultraviolet. Then I go through X-rays and gamma rays. So my visible light spectrum is divided into different wavelengths, which represent colors. What? I liked this diagram as well because it actually shows you the wave. So I can see at the red end of the spectrum, the distance between crest and crest, which is my wavelength, is longer than at the purple or the violet end of my spectrum. The distance between crest to crest is smaller. And then I get to the ultraviolet, beyond violet, and the infrared, beyond red. And so as you're looking at this visible light spectrum, what do you notice about the colors, and what observations are you make? And as you look at this, what color on this spectrum do you think seems the brightest? Which color has the brightest appearance to your eyeballs on this computer screen? And how about the least bright? So I'll give you a few minutes to think about that. Now I want to show you a demonstration. We would have done this in class, of course, and I have a little card that has a piece of plasticky paper that has different measurements, I want to say, on it. It's different widths for dividing up light. When light hits a surface and bounces directly back, that reflection is usually equal to the angle of incidence. Well, what happens with the visible light is I get the light from the sun, which for us we can call, white light, regular light. Everything's combined. I can't see the colors. And that light gets divided, refracted into different wavelengths. All of a sudden, I start to see the different colors. So I'm going to go to this video first. And it's muted here, so I'm just going to show you. Here's this little
Observe
card.
how your teacher split white light into the colors of the visible spectrum. List the colors that you see in the order that they appear.
So you can just talk about them, to yourself. Go, oh, here's the colors I see in the order that they appear.
Describe whether the colors blend from one to the next or have distinct boundaries between them.
What are you noticing between the boundaries? Are you noticing that it's like, here's red, here's orange, or is there some blending?
Which color of light seems to be the brightest? The least bright?
So on that diagram, you were looking at which color seems the brightest, which seems the least bright. What do you notice about the boundaries? Now, with the electromagnetic spectrum and with energy, microwaves harmful to humans. Microwaves are over here. So what do you know about microwaves? Are they harmful to humans? And then the next question was, how about X-rays? So microwaves are here, X-rays are here. So thinking about what's the difference between those two waves and which, if either, maybe both, is harmful to humans. Now for part B of this experiment, we have these things called phosphorescers, and they're super, super awesome and cool. And it's basically a cardboard box that looks like this. In that cardboard box, you will see...
Part B, color light. Sketch and describe what you observe.
So, and you would have opened your box and you would have looked at the inside of the box and you would see this strip of kind of like sort of yellowy, chalky kind of paper. There's some phosphorus on there. Think about the phosphorus that's in, when you strike a match, that has phosphorus on it.
After the star-shaped cutout has been exposed to light for 20 seconds, remove the cutout and observe.
So what you would have done is you would have opened that little box, it has a lid on it, and you would have put the star-shaped cutout in the bottom of the box. If we go to here, we would have, so the lid is on the other side. And then we would have inserted the card on the bottom and we would have turned it over to open the lid so that the light could hit that specific spot on the phospho box. And we know that light is on the electromagnetic spectrum. Light is carrying energy. That energy is being transferred through the, in our case, air. And so when the light hits that phosphorus star-shaped spot, what's going to happen?
Observe and record what you see.
So we pulled out the card and we put the lid back on and we looked inside the card, and what we saw was this. So you'll notice it's kind of glowy. Whatever phosphorus chemical composition was in that strip um, sucked up the energy from the light, and it only sucked up the energy from the light where the star-shaped cutout was. Pretty darn cool.
Colored film card. Describe or sketch what you see. Rank the colors from brightest to least bright.
So the next step would be take out the star-shaped card. The star-shaped card was blank. It didn't have any film on there. Now we're going to put in this card, which has different colored film based on the visible light spectrum and based on different wavelengths. So we see we've got red, orangish, we've got the plain cutout, we've got yellow, green, blue, violet. So now, if you were to describe or sketch or think about which color on this spectrum, and this is a prediction, do you think is the brightest, colors, or color? So you're going to rank which colors from brightest to least bright. So you've got red, orange, white, yellow, green, blue, purple, or violet. I don't care. I'll know what you mean.
Describe or sketch what you predict will happen if you use the colored film card instead of the card with the star-shaped cutout.
So you know how we just had the box and it had the phospho strip, and we put the star-shaped cutout in there, and when we exposed it to the light in the room, that light transmitted energy and glowed the little phosphorus spot where the cutout was. So if we do that same thing, and instead of using the star-shaped cutout, if we put in this color strip, you know that the light from the room is going to shine into the box, and we're going to let it shine for about 20 seconds to transmit that energy. Which of these cutouts is going to have the most energy? Which of the cutouts will accept, refract the most energy onto that little phosphorus strip?
After the colored film card has been exposed to light for 20 seconds, remove the colored film card and observe. Rank each color and the cutout shape according to how brightly it colored.
Now, this is my favorite part. I love this part so much, and I so wish we could just be together so I could watch you experience this part. We are looking at the piece of phosphorus strip. What has happened is we exposed it to light, we put the lid back on, we took the color cards out. No, we left the color cards in, and we looked in there, and now we're looking at which color has the most energy, which color is the brightest. And I bet you many people were wrong. It's my favorite part. I love that. I was wrong too. Did you think yellow was going to be the brightest? How about orange? They're pretty bright. But what you're going to notice is which colors have the most energy. Brightness equals energy. Which color has the most energy is a direct relationship to frequency, which is a direct relationship to wavelength. So it only makes sense that the wavelength that has the most energy is the shortest because it has the highest frequency. And when we look at this wavelength in this visible light spectrum, we're going to notice that violet is the highest energy color. in the visible light spectrum? Red is the lowest energy color in the visible light spectrum. So here's that again. And when we look at the colors, which are the brightest, and how do we explain that? So, which characteristics of light wave explored in this activity affects the amount of energy that it carries? And so, there's a question for you to think about and to sort of synthesize the information that we've learned about. It's been a lot, and I know, and I'm trying to repeat and slow down and give you time. And there's no rush, so please rewatch a segment if you want to. So, go ahead and answer this question. Here's another question. Based on your facts, based on your information, based on what you know about wavelength, frequency, and energy, which color is more likely to damage your eyes because of the higher energy? What would you say? Thanks for hanging in there. I apologize for not being able to post yesterday. I know you were devastated. The internet's back up and working, and hopefully, we won't have any problems here in the future. I miss you, and I'll see you soon.